awful lot of people know that.
Absolutely not.
I just don't, because in some jobs where we would have, say, two floors of normal loading, and then you'd have a major transfer structure like 750 thick, or
oh yes.
And it's just like, if you back prop, say, like normally with basement, car park, ground floor, you might have a first floor, then you have a transfer structure. If you back propped right down to the basement, does that take out, so you're not allowing the slab to settle, so you're actually kind of pretending that you're taking the...
You are sort of, however, there is a little trick you have to do, because you have to try and get rid of the possibility of elastic shortening. And the way you can do it by preloading all of the props.
But is it a case of actually leaving the props there? You know, that you don't take them away to back prop them, you actually prop them and insist that they actually stay propped.
Well, the problem then is your load could end up being cumulative. So the idea normally of back propping is you allow the slab to take up its deflected shape, because there are systems where when you've got your force work scheme, you pour your concrete, and then what you can do is, I just got a couple of people to admit, you can take your deck out, but the actual props remain in place. So the prop has got 4 clips around the top. You release the clips, it allows the decking system to drop, to be removed, but the prop itself will remain. And then it can act as a back prop. But what you have to do there is you have to allow the slab to take up its deflected shape. If the props remain in place locked, the slab isn't allowed to deflect. Load is in the props. So when you pour the next one, more load in the props. So what they have to do is release the props first, allow the slab to deflect, so you transfer the load back to the columns, and then tighten the props back up again.
A 750 deep transfer slab. I mean, there's no slab underneath that's going to support that.
Oh, absolutely. What you then have to do is, do you remember the job I told you about in Birmingham, where the basement slab was suspended board? What we ended up doing was using a completely different force work scheme, and we basically had to span the loads back into the pile caps.
Is there wording on a spec that covers this? Because I'm not aware of this problem, and it was actually frightening.
I don't think there is.
I say, like, I mean, there's a few things there about, like, restraint that ought to be in specifications, and they're not.
They should be. I can't disagree with you on that one. I can't disagree with you on that one. I mean, there's so many things that I think. I mean, temporary works really is just a hit. It's not mentioned really in specification. It's not an item on a bill of quantities.
But it's the thing that's likely to fail.
The thing that's most likely to fail, I would argue.
Bit of an eye-opener.
If
I assume all the solutions arrived today.
I'll tell you what you might be interested in, Peter. Go on the website for the organisation that did the original research. See if I can remember the web address. It's the Concrete Society.
There's a Temporary Works Federation that I've come across.
Temporary Works Forum. I'll mention them in a minute.
Yeah.
But look at this website. I can remember what it is. It's construct.org.uk. And what you can do is you can download the original research that they did. They produced these little leaflets all about concrete frame construction. I'll tell you another one you'll be interested in is how soon after pouring so I think 250 thick concrete slab, columns either 8 or 6 meters spacing, so just box stand special, not post-tensioned or anything like that. How soon after pouring the concrete you think they were striking the soffit, removing the soffit system?
Well, I think the normal is about a week. Like you're mentioning days.
Right. Would you be surprised? Would you be surprised if I told you they fully struck the slab, removed all of the supports, 19 hours after the cement and the water met at the batching plant?
They were feeling lucky.
As a colleague of mine was involved in the research, and he told me all these university professors turned up, and I had a load of boys there to take all the props away. The boys made the professors stand underneath the slab with them when they started taking the props away. So they simply didn't believe that it wouldn't collapse. The way they did it was they changed. The idea is you have to know the in situ strength of the concrete, not a concrete cube being artificially sort of prepared, artificially cured and tested in a laboratory. You test the actual concrete in situ. And there's two ways of doing that. The first one is something called a lock test, LOK, which is like a little pull test on the concrete. And you can relate the tensile strength to the compressive strength in situ. The second one is thermocouples. And the is when you mix cement and concrete together, as the concrete cools, it gains strength. So there is a relationship between temperature and strength of the concrete. Google it, it's called maturity testing. You use thermocouples. It's a fraction of the cost of, and we use it for early age striking. It's not for 28 days. So you still have to do your cubes for your 28-day strength compliance, but it's to allow you to move all your temporary works. It allows you to strip it and move it on a lot quicker than you would normally do. On crack widths with crack theory. There's a lot of research has been done on this, Peter. So have a look at this website. You'll get a lot of information from there.
Yeah, as I say, that was an eye opener.
It's good stuff. Right, morning everyone. I think we're still waiting for one or two more people. I think.
Morning, Ray. I just wondered, is there any chance of getting the guys to keep their cameras off while you do the lecture? Because if anybody's got some background noise or whatever, their camera kicks in or their video becomes active and then cuts you out.
Ah, okay. Well, maybe the trick then is to mute. I think they need to mute. I think that's the. I can actually mute people if it's disturbing you. So I will, if I can hear any noise, I'll make sure. Well, I'll just ask people to keep themselves muted unless they want to sort of offer up any questions or anything.
Okay, thanks.
Just checking people's names off as we go. So, morning, Gift. Phil Thorpe is here. Ashley, morning, Ashley.
Morning all.
Morning, AA. Enrique, good morning, Enrique. Morning, Leo. Ian. Daryl, morning, Daryl.
Morning, James.
Amjad, morning, Amjad. Stefan,
Morning.
Stefan. Mr. Brown, Mike Brown, morning, Mike.
Good morning, Ray.
Dashi. So I think we're just missing Derek, I think. Let's give him what we got, give him another minute. Whilst you're waiting, gents, can you try and find design module 4 in your course notes? The section will be 064. It's the design of it's wind load and hoardings. So section 064, 64.
If you could, maybe Dushi and Ao can keep their mics off.
Right, I think we're all here now. Morning, Derek. So if you find section 064 in your course note, just give me a thumbs up if you've managed to find it in your course notes, please. We'll say design module 4, the design of hoardings. Okay. Welcome back, everyone. We're going to start off this morning looking at wind loading. And the example we're going to do is for a site hoarding. But wind loading, we would use exactly the same calculations if we wanted to check a piece of formwork, shuttering, make sure shuttering doesn't blow over in the wind. Sometimes we have problems with stability of cabins, site cabins. If you're in a very windy location, there have been cases where cabins have been blown over. So sometimes you might need to do a stability check on cabins. Scaffolding. If you think about it, if you put a load of sheeting on a scaffold, again, you've built an enormous great sail. So any item of temporary works which is affected by the wind. After coffee, we're going to start looking at foundations for machinery. So we're going to look at how we design foundations for mobile cranes. We'll then look at what we do for machines with tracks, so for piling rigs. So we'll do a little method for the design of piling mats. After lunch, we'll do a little bit of steelwork design, and we'll do an example of needling. So if you need to support some brickwork to put a new steel lintel in, show you how we can design up the temporary works for that. And then normally at the end, we'll have a little sort of open session, sort of anything else that you guys might want to discuss. Okay, and the idea is we'll try and finish somewhere around sort of 4 o'clock today. Okay, now I'm going to start off this morning with a little video for you. This is a video taken in the Republic of Ireland. There was a big storm that went through Ireland a couple of years ago. And this was caught on somebody's security camera. It's in their back garden. Look at the way, I'm hoping I'm sharing this properly. Can you see some houses and a fence? Okay, just have a look at what effect the wind has on this fence and the way this is going to fail. So can you see, gents, there's two sort of modes of failure there that we need to consider. First of all, there is a structural failure of the actual posts themselves. If you keep doing that, if you put sufficient bending on it, the posts could fail in bending. Secondly, it's got some sort of foundation underneath it. So what we normally do is dig a bit of a hole, chuck some concrete in the hole, and put the post in the hole. If we don't make the hole big enough or deep enough, then there's a possibility the foundation will fail. Okay, so in effect, there's a couple of different modes of failure that we need to consider here. Now, how do we work out the wind? We're going to look at this module number 4. Let's turn this off. Get this module 4 loaded. Just share this with you now. Screen. So I'm hoping you're looking at something that says wind load and hoardings. Okay. Now, this is the sort of thing we're going to be considering. So, but it equally applies to any item of temporary works which is affected by wind. So cabins, formwork, scaffolding, it's exactly the same process. Now, obviously, we're going to be designing for wind. You might also be asked to consider something called crowd loading. I'm sure many of you as structural engineers would have been involved with crowd loading. And crowd loading represents people leaning on it or perhaps falling against it, or I suppose debris maybe being blown against it. Okay? I'm sure you've all seen it. If you get quite a strong wind, you could have tree branches thrown against your hoarding. I've actually seen this. I was driving once through London quite a long time ago. There's quite a real windy day, and there was a big plastic dustbin, you know, the sort of thing you put your garden waste into, and it just got blown across the road. It hit the curb on the other side and went flying into the hoarding on the other side of the road. But it basically, just the wind caught it and just blew it straight across the road. Big plastic bin. Crowd loading is not the same everywhere. Okay? We get the loads from, how many of you gents are familiar with codes of practice for design of handrails? Things like that. Yeah, I'm sure most of you would have been involved with that. And the handrail code gives you different magnitude of loading depending on how likely a big crowd is. Okay? So if you're in the middle of the countryside, it's pretty unlikely you're going to end up with a big crowd. But what about this example? This is one I was involved with. So I was designing this hoarding. They provided a design brief. It had crowd loads on it. I had never seen crowd loads that big before. So I phoned up the site and said, what's going on? Why have you got such massive crowd loads? It's to do with this thing here. Okay? This particular job is in a city called Sunderland. Now, if you happen to live in Sunderland, does anyone know what this structure here might be called? If you live in Sunderland, what would you call it in Sunderland? Does anyone know? Right, it's called the Stadium of Light. If you live in Newcastle, what would you call it? The Stadium of Shite. So, gentlemen, what we're looking at here is Sunderland Football Club. Okay? You can imagine what these crowd loads represent is 5 o'clock Saturday afternoon, the match is finished, Sunderland have lost to Newcastle at home, like 5-0 or something, all a crowd come out, and then it kicks off. Okay? And I mean, it properly kicks off. So this hoarding is designed to withstand a Geordie riot. Okay? So can you imagine a crowd loads for something like this are going to be very, very substantial. But if you had a project in the middle of the countryside, I mean, literally 5 miles from the nearest building, you're not going to have a big crowd load. Okay? So are you all happy that you understand that crowd load can vary on, are you in the city centre? Are you in the middle of nowhere? Now, what we're going to have is plywood sheeting. We're then going to have horizontals, which we're going to call rails. And then we've got verticals, which we'll call posts. And when you look at it, it looks a bit like a piece of shuttering, doesn't it? Where you've got your plywood. In a shutter, the horizontals we called secondaries, and the verticals we called primaries. In a hoarding, we're going to call the horizontals rails and the verticals posts. In effect, it's a bit like a hoarding, a bit like a shutter. Now, can you see in this particular example, we have dug holes and these posts have been concreted into a hole in the ground. Okay? So you can either dig the hole by hand, get some men with shovels and dig it, or you get a little machine with a drill on it, drill a series of holes, put some concrete in, and drop the post in. Okay? So I think it really depends on how many holes you've got to drill. If you've only got to do 10 holes, you probably just get some men with shovels. If you've got to do 1,000 holes, it's probably quicker and easier to get a machine to drill them for you. Okay? Now, there will be some occasions where your client will not want to or will not be allowed to drill holes. Why? Why might they not want to or not be allowed to drill holes?
Trade services.
Yeah, maybe you've got lots of buried services underneath where you want to put this. You know, you've got gas mains, you've got water pipes, you've got electricity cables, or maybe you're in a city centre on a footpath and you don't want to start drilling holes because then you've got to repair all the holes you've drilled. So an alternative is to use Kentledge. Now, I quite like these methods where they use concrete blocks. I'm less keen on these where they use drums, and I definitely would not fill these with water. 100% I would not fill them with water. What could be the issues if you start filling those drums with water? What sort of risks are we creating?
I'll empty it.
Yeah. Could it perhaps leak? Could, if it gets hot, maybe the water starts to evaporate. Yeah. And you think about it, that hoarding could be there for a couple of years, 2 years. What have you got in those drums after 2 years? If you fill them with water. Gentlemen, what you've created is a major biohazard.
Legionella.
Absolutely. Yeah. I mean, you've got all sorts of stuff in there. Vials disease, Legionella. It is stinking, stagnant water. It's a major biohazard to try and dispose of it. It's a real problem to try and get rid of it. So what could you fill those drums with, perhaps, instead of water? What about filling them with sand, soil, rubble? Do you know what? I don't care what you fill it with, as long as it's heavy enough and then it doesn't want to leak. Okay? It's normally quite a good one to fill it with. Okay? So you can either drill holes and concrete the post in, or you can use Kentledge. Very occasionally, you may end up with a project where you have to put a hoarding next to perhaps a railway line, or if you're working in London Underground. What you then have to start considering is suction loading. Has anyone ever been involved with projects involving rail? As a train or a tram goes past, you generate suction behind it, and you may have to start designing your hoarding for suction loading. We spoke about sort of risks and stuff yesterday. We said risk classes, we call them very low, medium, high. What risk class would you put this sort of hoarding into?
High.
Yeah, I think because of the location, this is high risk. What sort of category of design check would you have to go through here?
3.
Category 3. And would you also suggest that the railway people or London Underground will also want to approve what you're doing before they allow you to build these hoardings? Absolutely. So do you know what I mean, Jed? You've got an extra level of procedure to go through because Network Rail will want to put their own checking onto this as well. And that Network Rail check, those of you who've got some experience in Network Rail, how long can it take them to check and approve something as simple? Absolutely, you could be looking at months. It is not unusual for them to take months to approve your hoarding. Okay? It is a major pain in the backside. Yeah. Now, so if you're on in a city job, maybe you've got issues with noise, from your you don't want to upset your neighbours. You could start turning your hoardings into acoustic barriers. And things like polystyrene are very, very good as acoustic barriers. You can simply connect polystyrene to it. Or there are a number of proprietary systems, like the one on the screen, which is there to help reduce the noise coming off your construction site. So certainly in city centres, this is an important consideration. In the middle of the countryside, you wouldn't be worried about this. Make as much noise as you want. Okay? In a city centre, it is a big issue. Now, one thing to avoid, make sure your site don't dig a big hole next to where your hoarding is. Okay? This is a hoarding I designed this is the company I used to work for, Kier. It's in Milton Keynes, so I took this photograph. I designed a hoarding. What they didn't tell me was they had a big basement excavation on the other side of the hoarding. Okay? So they simply cut the ground. They cut the ground a little bit steeper than they should have done. The ground started to move. So can you see on the right hand side here, the ground is starting to move, and the hoarding is starting to collapse onto the site. This was put in by the site as an emergency measure to stop the hoarding collapsing onto the site. So make sure they don't dig big holes next to where you've designed your hoarding. And finally, you don't have to do it with timber. There are lots of proprietary systems where you can simply hire this sort of thing to go around a project. There's lots and lots of companies that do this sort of thing. But be very, very careful. Whoever you hired it from, they will give you information about what sort of wind speeds these sort of systems are suitable for. So I'll give you a wind speed. And it might be your job actually to check that for that particular site, you're not likely to exceed that wind speed. What you'll find, for most sites in the UK, you will exceed the wind speed for this sort of stuff. Okay? So in my opinion, there are very, very few sites in the UK where this sort of stuff is suitable. In your country, Peter, in Ireland, I would be very surprised if there was anywhere in the Republic of Ireland where these sort of systems were suitable. Because I hope you all know the wind speeds in Ireland tend to be a little bit higher than they are in Great Britain. So I'd be very surprised, Peter, if there were many places in Ireland where this was suitable. I've done quite a bit of work on these sort of systems, and you could put sufficient Kentledge on it to stop it falling over. That's not a problem. The metal framing, on the whole, tends to be just about okay. For me, the problem is the way the sheeting is joined to the framing. Okay? It's spot welded. Okay? The welds are tiny and they're really, really bad quality. These are made really, really cheap, so the quality of the welding is terrible. But what tends to happen is when you get a decent wind, okay, the sheeting just wobbles around. Eventually the welds break and the sheeting simply starts to peel away from the metal frame. Okay? And it's simply down to the size and the quality of the welding that's used. It's shocking quality. Okay. So, gentlemen, what do you think affects the magnitude of wind? Why would wind be higher or lower? What affects wind? Exposure. Now, what do you mean by exposure, Peter? Be a bit more specific. Give me one example of what you mean by exposure.
Valley.
So again, you're very quiet.
Top of a mountain in a valley.
Yes.
Between tall buildings.
So, topography. Okay? What happens to wind speeds, gentlemen, as you go up a hill or a mountain? Increases. So, altitude and topography. So, are you in a valley? Are you in between tall buildings? Yeah. Are you on top of a hill? So, exposure. What else affects wind speeds? Sorry, say that again.
Ground roughness.
To some extent, yes. In particular, what around your site might be able to offer some sort of shelter from the wind. Okay, so sometimes tall buildings can offer shelter. Okay, trees can offer shelter. Okay, water doesn't. So if you're next to a big stretch of water, really there's nothing there to break up the wind. The wind will just come whistling across the water. There's nothing there to break it up. Okay, what else can affect wind? All right, what about postcode? Where you are in the UK and Ireland. Okay? I'll show you what these things look like in a moment, but we have these things called wind maps. Okay? And there is a wind map that covers the UK and Ireland. And every country has got its own wind map. So if you're working in France, France has got a wind map. Germany's got one. My family come from Poland. Poland's got a wind map. Okay? And in the UK and Ireland, if you imagine London, the southeast of England, London area, is the least windy part of the UK. What happens to wind when you go north from London or west from London? What happens to wind speeds north or west from London? Increase. Okay? So, as I said, Peter, if you're working in London, the wind speeds are very different, for example, to if you were working on the west coast of Ireland. If you were in Galway or Kerry or somewhere like that, you've got far, far higher wind speeds. What about proximity to the sea? What happens to wind speeds when you get nearer the coast? They increase. Okay? And one other thing that we can take into account, for temporary works, there is a statistical factor that we can utilise. Okay? And the argument is like this. If you design a piece of permanent works, a building or a bridge, you might have to design, for example, let's say a 1 in 200 year storm. Okay? If you design a bridge and the life of that bridge is 100 years, you've sort of got a 50-50 chance of your bridge or building being hit by this 1 in 200 year storm. So would you agree the probability is quite high? Yeah? If you've got an item of temporary works, which is only there for a short period of time, I mean, for example, shuttering, it might only be there for a few months, would you agree, statistically, the probability of your shutter being hit by a big storm is very much reduced compared to a bridge or a building? So we can take statistics into account as well. So these are the sort of things that we need to know. So first of all, location of the site. So the postcode. Okay? We need to know the geographic location of the site. Secondly, we need to know, rough. We're not saying to the nearest sort of centimetre, but we've got to have a rough idea how close or far away you are from the sea. So your client needs to tell you, or you can look it up on Google Earth or something like that, where the site is in relation to the coast. Okay? Now, we then got to know how much shelter is offered. So are we in the town centre? Are we out in the countryside? Okay? We'll look a little bit more at that in a moment. We then have a topography factor. So are we in a valley? Are we halfway up a hill? Are we on top of a hill? Okay? Altitude. We need to know the altitude of the site in relation to sea level. Okay? So your site you need to know what the altitude is. Generally, the higher the altitude, the higher the wind. Duration. So this is the statistical factor. Now, I will explain to you in a moment why this is now incorrect. Okay? But just give me a moment, I will explain that to you in one moment. And then, for example, if you're looking at something like scaffolding or false work, have the site put some sort of sheet. Okay? So this is the sort of information we need. Now, we then have a a method to work out the wind. I would imagine most of you will have some experience of using Eurocode 1, which is the, what do they call it, actions or something? Us old people call them loads. Eurocodes, I think, call them actions. But there is a method in Eurocode for working out wind. Who's got some experience of Eurocode, working out wind to Eurocodes? How many of you gents have done some little bit of wind calculations? Oh, okay, one or two of you have. The method in Eurocode is quite complex because you can take into account lots and lots of different variables. So, for example, Gift, I think you can consider the season. You can consider the prevailing wind direction. So is the wind coming from the east, from the west, from the north, from the south? You can consider the shape of your building. Yeah? Is the building, for example, if it was a chimney, okay, it's quite aerodynamic. Whereas a building, a big long building, is not particularly aerodynamic. Okay? You can also consider things like surface roughness. So if your building is clad with some sort of steel or aluminium sheeting, it's probably quite smooth. But if it's brick, it's not very smooth, is it? So there's lots and lots of different factors we can take into account. Okay? There is an organisation, however, called the Temporary Works Forum. Okay? Make a note of this web address, gents. So the website is twforum.org.uk. Right, just make a note of this somewhere. Don't forget it. We are a registered charity. I'm one of the founder members of this organization, and we represent sort of the temporary works community in the UK. There is also a branch now in Australia. There's one in New Zealand. There's also one in the Middle East. Now, I can't remember which Middle Eastern country it is. I can't remember. It might be in Dubai, I think. Okay. There's also one in Hong Kong. So there's a number of these temporary programs being set up around the world. Okay. And we produce guidance. Just bear with me a second. This is what we produce. Okay. You can go on that website. You can download this for free. Okay? We are a registered charity. We don't want your money. I mean, if you send us money, we won't mind. You know, Gift, if you've got too much money, please send it to me. You know, if you don't know what to spend it on, I'll spend it on. Okay. So we are a registered charity, and we produce these guidance notes. They are free. Go on the website, click on the bit that says publications, and you can download them for free. They are free. Okay. Now, the original one of these came out in 2010, I think it was. This has just been revised. Okay, this is the new version. I think this was published about 2 or 3 weeks ago. Okay, so what I'm going to tell you now is slightly out of date. Okay, but I'll explain what the difference is. Okay, this tutorial now is very slightly out of date. Okay? Now, the method we're going to use is the method in here. Okay, so I did the revision, so I know what the changes are because I was paid to do the revision. And it's a simplified method compared to what you do in the Eurocode. And I'll explain what the simplification is. Okay. Now, first of all, we have a basic formula for calculating the wind pressure. And the peak velocity pressure is a probability factor squared multiplied by this number here, 0.613. If you want to know what that represents, read this bit down here. Okay. Now, this is the simplification. We use something called a combined exposure factor. Okay. What we did was we went through Eurocode and we looked at all the different variables that you can have that might apply to a hoarding. And we basically took an average value, so we ended up with one number, okay, and we called it a combined exposure factor. So what we did is we multiplied about 10 different factors from Eurocode and ended up with one number, okay, which applies to hoardings. We then have this S-wind factor squared. Now, in the original guide, for temporary works, what we could have was a probability factor where we used to say if your temporary works are in position for less than 2 years, we can use a probability factor of 0.83. Now, when you square 0.83, it comes to about 0.7. So for temporary works, we used to say if it was there for less than 2 years, you can reduce the wind by about 30%. Okay? This is one of the big changes. In the new documents, and this will be reflected in BS 5975 when that's revised next year again, there's been some research, and I think it's based on sort of climate change. What we're finding is that increasingly we are statistically more likely to be hit by a big storm. Okay? Because of climate change, the big storms are becoming more severe and they're going to be more frequent. Okay? I think you all listen to the news. Climate change happens. The big winds are going to be stronger and more frequent. Okay? So we have to allow for that in our wind calculations. So, in the new guidance, the probability factor has changed. The maximum length now is 1 year. So if your temporary works are there less than 1 year, we use a probability factor of 0.9. Okay? So if you square 0.9, it's, 0.81. Okay? So the two changes are, the probability factor now is 0.9, and it's only there for a maximum of 1 year. Okay, so just bear that in mind, gentlemen, when we're doing this tutorial. Okay. So first of all, we have this formula here. QP, probability squared, 0.613, combined exposure factor, S-wind squared. So now we have to work out what S-wind is. And there's another formula for that. S-wind is your basic wind speed for your geographic location, multiplied by a topography factor, multiplied by an altitude factor. And the altitude factor is 1 plus the altitude of the site divided by 1,000. Okay? Just write this down or try and remember it. So your pressure is this formula here. And to work out your S-wind, you use this formula here. Okay? Hopefully you can all understand this. All right. So let's have a look at where we get some of these factors from. Now, your basic wind speed, VB. What we do is we read it off a map. So this is the wind map for the UK and Ireland. And can you see the southeast of England, sort of the London area, is the least windy part? Can you see as you go north and west, the wind speeds increase? And so as I said, Peter, if you're working, out here somewhere, the wind speeds are a lot higher than they are in central London. Okay? So that's why you need to know the postcode of your site. You need to know whereabouts in the UK. Okay? Secondly, we have this topography factor. Now what we do is we look at the terrain. So your site needs to give you some idea about what the terrain looks like. The lowest factor we have is 1.0. And what we're saying there is the ground is pretty flat. Okay? The highest factor we have is 1.36 if you're at the top of a hill or a cliff. So can you see that one factor varies by 36%? Yeah? So that's a lot. That's a big difference. Now this is the combined exposure factor. So this is where we looked at Eurocode, we looked at a whole load of different factors, and we multiplied them together to give us one number, that applies to hoardings. And the way this chart is split is we look at the height of what we're designing. Are we in the countryside next to the sea, or are we in a town? And then the distance to the nearest shoreline. How close or far away are we from the sea? Okay? And then we read off the graph. Now you can interpolate between the numbers. So if your site happens to be sort of 50 kilometers from the sea, you're going to be somewhere between the 10 and the 100. So you can interpolate between the numbers. Right? Now, this is where we've got to be a little bit careful. Who's struggling to hear me? Are some of you struggling to hear me?
It's only me, Ray. I had a poor internet connection on site, so just restarted back again.
All right, okay.
Now much better now.
Is it okay now, Amjad?
It's okay, yeah.
Right.
I missed a few things, but it's okay. I think I've been covered in the previous class. I think stuff. So I'm just
Okay.
yeah. Thank you.
No problem, sir. All right. Now, this is where we've got to be a little bit careful. What do we actually mean by next to the sea or countryside or in a town? So we've got to be a little bit careful to understand this. Okay. If next to your project you have a stretch of water more than 1 kilometre wide, it counts as being next to the sea. Right? I'll give you an example. I live basically right in the middle of England. I live near Northampton. I live between Bedford and Northampton. Now, not far away from where I live is a big reservoir. It's called Pittsford Reservoir. It is about as far away from the sea as you can get in the UK. And it's virtually the furthest point from any coastline in the UK. But Pittsford Reservoir, it's about 5 kilometres wide. So if we had a project doing some sort of work next to Pittsford Reservoir, it would count as being next to the sea. Okay? Even though we're as far away from the sea as you can get in the UK. Right? The next little bit of confusion is, in order for your site to count as being in a town, you have to be more than 2 kilometres from the edge of a town. Okay? So your site could be right on the edge of Manchester or Birmingham or Dublin or London. Okay? If it's less than 2 kilometres from the edge of your city, it counts as the countryside. Okay? So be careful with that. You've got to be more than 2 kilometres from the edge of your town for it to count as a town. Now,
All directions.
Sorry, say that again.
From all directions.
Absolutely. Yeah. The other thing to look out for is if you've got a big forest next to you. So, for example, in the middle of the UK, we have this thing called Sherwood Forest. Now, you've all heard of Robin Hood, haven't you? Okay, that's where Robin Hood used to live, supposedly. Okay, it's one of the last remaining large forests in certainly in England. There's quite a few big forests left in Scotland and Ireland and Wales, but very few in England. If your project is next to Sherwood Forest, it counts as being in a city centre. Okay? Because the trees, a load of big mature trees break up the wind. So if you had a job in the middle of the forest, it counts as a city centre. Okay? So be careful, gentlemen, exactly what we mean by countryside, exactly what we mean by a town centre. All right? Now, we then have rules about crowd loading, and we get that from the footpath code, from the handrail code. And you might sometimes have to design for suction from trains. Okay, so this is the sort of thing we're going to look at design. And we're going to look at module 4. Okay? Now, in module 4, we are going to do 2 examples. And the reason we're going to do 2 examples side by side, often people ask me, they say, why can't we have a standard detail for a hoarding? Why do I need to pay for a design every time I want to put up a hoarding? Why do I have to pay for one? Why can't we just design a hoarding and then I can use it on every one of my projects in the future? Okay? Why do I need to pay you to design it every single time? Let me show you why. Yeah. And I'm not trying to do you out of a job here, AO. Okay. Let me.
The location. I mean,
Yeah. It's very, very difficult. Yeah. Let me demonstrate to you why it's in my opinion, it's virtually impossible to come up with a standard detail for a hoarding. Okay. And we're going to do 2 examples of jobs that I worked on. The first hoarding is, and they were both jobs that I did when I worked for Kears. The first project was right in the middle of Oxford. Okay? We had a job for Oxford University, and it's called the Ashmolean Museum. It's basically right in the middle of Oxford, and we had to put up a hoarding around this site to do this particular project. Okay? Now, in the centre of Oxford, you've got shops, you've got students, you've got bars, restaurants. Would you expect to have to design for a bit of crowd loading? Yeah, I think that's not unreasonable. Okay? The second project was at a place called Milford Haven. Now, if you don't know where Milford Haven is, it's the very, very far tip of Western Wales. Okay? If you want to go any further west, you will get wet because you're in the Irish Sea. Okay? You really, really can't go any further west. And we had a civil engineering project. What we were building is a jetty into the sea, and it's where liquid gas comes into the UK. And so we built this jetty, it's about a mile long into the sea. A big sort of boat arrives with liquid gas from Kuwait or Saudi Arabia, wherever. It docks up against the jetty, and then they pump liquid gas to these big storage containers on land. Okay? And our site compound was on top of a 20-metre cliff right next to the sea in the middle of nowhere. Do you think we might need to design for any sort of crowd loading on that sort of site? What do you reckon is the biggest crowd you might get on that sort of site? Well, probably seagulls. Okay? There's nobody goes there, so you're not going to have a crowd loading. All right. Have you all got module 4 open in front of you? Okay. So let's follow these numbers. So let's look at Milford Haven to start off. Okay? Let's go back to our map. Now, Milford Haven is, can you see where my arrow is pointing on the screen? Milford Haven is about there. Okay? It's about as far west as you can go. So my basic wind speed, if you look at these lines here, I'm hoping I've taken the basic wind speed for Milford Haven of 24. Okay? Somebody just give me a thumbs up that I've taken 24 for basic wind speed for Milford Haven. Yeah, good. Okay. If Oxford is here, And I'm hoping for Oxford, I've taken 21.5 as my basic wind speed. And so can you see those numbers in the calculations? Good. Now, topography factor. If you ever go to Oxford, the ground is flat. And you're in the Thames Valley, it's basically flat. So, for me, this top one is the nearest representation. So I'm going to take a topography factor for Oxford of 1.0, because you're in the Thames Valley. Now, Milford Haven. Okay? What we had was a 20-metre high cliff, and the hoarding had to go on the top of that cliff. So look at these diagrams. Which one looks the most like that? A, B, C, D, or E? Which one looks the most like that? E. Yeah. And if I put the hoarding at the top of the cliff, okay, up here, can you see I'm going to use a topography factor of 1.36? Okay. So can you see, gentlemen, the topography factor makes 36% difference to the wind. I mean, that's a very significant difference. Very significant difference. Now, let's go back to our combined exposure factor. Now, what we're going to have is the holding. So we're going to use plywood. We're going to stand the plywood up in that direction. Message is coming in. Yeah. Derek, I think you keep losing the sound. I think that's your internet connection. Is anyone else losing the sound, or is it just Derek? The rest of you okay?
All good this end.
Yeah, I think if you're there, Derek, I think it's your connection, my friend. Oh, it's back again. All right, good. Okay. What we're going to have is a sheet of plywood high. So it's going to be, what did we say yesterday? What's the height of a sheet of plywood? What's the long dimension on plywood? 2.4 foot. Yeah? Now, to allow for the fact that the ground isn't exactly smooth, what we often do is put a little skirting on the bottom of the hoarding. So this would be something like a 100, 4-inch piece of timber, something like a 100 by 12, and we just put it on the bottom of the hoarding as a skirting. It just stops sort of vermin getting onto your site, getting underneath your hoarding. So if I said roughly the total height of the hoarding was about 2.5 metres, okay? Now, for Oxford, okay, so our hoarding is 2.5 metres high. Oxford is is miles from the sea. It is more than 100 kilometres from the sea. And we were more than 2 kilometres from the edge of the town. So can you see, for Oxford, I'm going to use a combined exposure factor of 1.06. Okay, 2.5 metres high, we're more than 2 kilometres from the edge of the town, and we're more than 100 kilometres from the sea. So I'm going to use 1.06. For Milford Haven, do you know what? We couldn't get any closer to the sea if we tried, could we? Yeah? We're very, very close to the sea. It's in the middle of the countryside. So it's 2.5 metres high, less than 100 metres from the sea, in the countryside. So I'm going to take a combined exposure factor of 2.03. Look at the difference, gents. In Oxford, 1.06. In Milford Haven, 2.03. That one factor has doubled your wind. Big difference, isn't it? That's a big difference. Okay? So let's go back to our calculation. So hopefully you'll know you can see where these numbers come from. Now, the basic wind speed we said was 24. The altitude well, the 20-metre high cliff. Now, this is the bit that we now would change. Okay, so if I was doing exactly the same example now, I would use a different probability factor. Okay, we've got 1.36 as our topography. So let's put it into the formula. So what we have is 0.83 squared times 0.613 combined exposure times S wind, where S wind is 24 times 1.36 multiplied by 1 plus 20 over 1,000. So that's 33.29. So we need to put that into there. So we got 0.83 squared times 0.613, 33.29 squared times the exposure factor of 2.03. When you do the calculations, it comes to 0.95 kilonewtons a square metre. Okay? So I'm just going to write that number down, 0.95. Okay? Let's do the same calculation for Oxford. So the altitude at Oxford we were given was 50 metres above sea level. So we got 0.83 squared, 0.613, 22.57 is the wind speed times a topography factor of 1 plus 1 plus 50 over 1,000 times a combined exposure factor of 1.06, and that comes to 0.228. And you can check those calculations yourselves at some point, gentlemen. Look at the difference between the numbers, gents. Okay? Sorry. Look at the difference between the numbers. For Milford Haven, it's 0.95. For Oxford, 0.228. We have a factor of 4 difference in the wind pressure. That is a massive difference. This is why, gents, it is virtually impossible to come up with a standard detail for a hoarding. Because if you design it for that pressure, how much of the UK and Ireland would that hoarding be suitable for? It's basically the middle of Oxford and nowhere else. If you design it for that wind pressure, your hoarding is massively expensive. And I'll tell you what's going to happen is your client is going to say, Gift, you've designed this thing for me. How much do you think this is going to bloody cost me to build? Yeah? Your customer will have a heart attack when they price what you've designed for them. So can you see, more often than not, it is cheaper to get a bespoke design to try and reduce the amount of equipment you need than it is to use a standard detail. So can you see why, and if you start designing hoarding, you will always get this question from your customer, why do I need to pay you every time I want a hoarding? Why can't you just design me one hoarding and then I can use it everywhere? Can you see why?
Yes, yep.
Yeah, because the wind varies by, a factor of 4. If we were up in northern Scotland, I reckon that would be a factor of 6. If you're on the west coast of Ireland, you might be looking at a factor of 7 or 8 difference. Okay? Massive differences in wind speeds. Just give me a thumbs up there. You can understand what I'm sort of saying. Does that make sense?
Right, could I just ask a quick question?
Yeah, sure.
You talked about the coastal sites, right?
Yeah.
Sometimes when you watch the news, you see when we have these storms, coastal storms hitting towns, and you see hoardings blowing over, because of the water.
Absolutely.
So is there sort of guidance on what you do in those sites for wave action on hoarding?
You would have to start going into marine codes and look at the effect of spray and wave action on hoardings. And you'll find it very, very difficult to design a hoarding for any sort of appreciable wave action. Okay? Because you imagine, you think about the density of water compared to the density of air. Okay? When the wind hits your hoarding, you've got a chance. If a big wave hits your hoarding, you're going to be in a lot of trouble then.
You think,
okay?
These things blow over quite regularly. You see them on the news.
Absolutely, because people haven't designed them to take the loading from being hit by a big wave. They just simply haven't considered that. Okay, so are we happy that we understand this calculation we've done so far? Right. So what we've done is worked out the wind pressure.
Sorry, Ray. Was the probability factor minimum 0.9? You said.
Yeah. So if I was doing a calculation now, this factor here would be 0.9 if it's there for less than 1 year.
Okay.
If it's there for more than 1 year, that factor simply becomes 1.0. Okay? So if you download the new hoardings guide, that's all explained. The reason I'm doing this, because all of this was, I sent all the course notes and everything before I'd finished revising this.
Yeah.
This has only been out, when did this get published? Probably about 2 or 3 weeks ago. Whereas I sent all the course notes and examples to the institution probably about 2 months ago.
Yeah, I'm actually doing a hoarding design now and using that guide.
So what you'll find is, how long are you going to be there for? More than a year?
No, month.
A month. Okay, so you can use a 0.9 factor. So when you square it, it's 0.81. So you've got about a 20% reduction in the wind.
Okay. Good.
Right. What we then have to do is look at the effect of the wind on the actual hoarding itself. Okay? Now, can you try and find this table in that module? I can't remember what page it's on. Somebody find it and tell everyone what page it's on this table.
Page 6 of 6.
So can you all have a quick look at page 6 in module 4? And what this table represents or shows is the effect of wind on the shape of the structure that we're looking at. So those of you who are familiar with wind codes, strange things can happen to the wind where we've got corners. So this could be the corner of a building, the corner of a bridge, the corner of your hoarding. You can start getting these sort of effects from the wind, these sort of eddy currents. The second effect is if you have some sort of opening. Okay? If you've got an opening in your hoarding, the wind can come through the opening and you can end up with a positive pressure on one and a negative pressure on the other side. You can generate suction. Okay? How many of you guys are familiar with these sort of effects from wind? Who's seen these sort of things? Yeah. What we can do is split the hoarding up into different zones, and they call them A, B, C, and D. And you have slightly different wind effects on different zones. And now we have two considerations. Is it a straight run of hoarding? So is your hoarding just a straight line? Or does it have corners on it? Okay? Now, most construction jobs, you'll probably have a square or rectangular hoarding around it. Okay? It's not that often where we would just have a straight line of hoarding. Most of them will have some sort of return. In terms of this, gents, is it likely that your hoarding might have some sort of hole in it, some sort of opening? Why would it have an opening, Gift?
Oh, if you got a gate or to allow,
It's called a gate, isn't it? Because if you don't put a hole in it, you can't get on the site. Yeah. So you've got to have some sort of opening in it so you can get lorries and people on and off the site. Okay. Now, the way I do this is I treat the corner. Let's use a different colour. I treat the corner and the area immediately next to the opening as a special case, and I normally design the hoarding for the worst case that is not a corner or next to an opening. And if you look at the way this sort of chart is set up, can you see the corner and the bit next to the opening, they call it the A zone. Okay? What I do is I design for the worst case that is not the A zone, which you'll find is the B zone, and then I go back and do a special design just for the A zone. And what I tend to do is in the corners, okay, in the corners we double up on the posts. So instead of having one post and you nail it from both sides, I'd have a post that way and a post that way. Okay, so you double up on the post in the corners, and where you've got the opening, what I tend to do is design up a special. So instead of using timber posts, I would use something like a square hollow section, a steel section, something like 100 by 100 by 4 or 5 mil thick square hollow section. And the reason I would use a steel post is because you can then weld some hinges to it, and you can hang a fairly substantial metal security gate on it. Okay? And you'd have to design that steel post first of all for the wind loading, any crowd loading, plus the weight of the gate hanging off the hinges. So you have to design the post and the welds for your hinges. And does that make sense to you? Can you see why I do that? And so it does save your customer a bit of money if you don't, because I know some engineers would just design the whole hoarding, treating it as the A zone. Well, I think you're wasting money there. Okay? I would probably do it as the B zone and then do a special on the corners and where you've got the open. So both our hoardings have returns on them. So we're looking at this section here. So do you remember I said let's ignore the A zone for a minute, okay? And if you look at the worst factor that's not A, it'll be this B, and the factor is 1.8. So can you see why I've taken it, and they call it CP net. I'm taking 1.8 as my factor. And then right at the end, I would do another design for that using a factor of 2.1. Okay, but that's a one-off little special design at the end. So can you all understand why I've done that? Why my argument for why I do that? You're all happy with that? Just give me a thumbs up if you're happy with that. Okay, good. Now we can then consider shielding effects. This is NETA factor. Now my advice to you for things like hoarding is ignore shielding unless you are 100% confident that you can include shielding factors. And my argument would be as follows. A lot of people say, well, I've got a hoarding, it's going to be here for the next 2 or 3 years. I'm going to take a shielding factor because next to my hoarding, I've got some really big trees that are going to provide some shielding, or I've got a building that provides shielding. Okay? Gentlemen, how can you guarantee, what 100% guarantee to me, that during the next 2 or 3 years, whilst your hoarding is there, those trees don't develop some sort of disease and the council have to come along and cut them down, or the building you're relying on shielding doesn't get demolished? How can you 100% guarantee to me that that's not going to happen? You can't. Okay? So my advice is ignore shielding unless you can 100% guarantee that shielding effect is going to be there for the next couple of years. Okay? Do you see what I mean, gents? Imagine you've got a big tree you're relying on shielding. The tree gets some sort of disease, Dutch elm disease or whatever, and the council have to come along and cut it down. Well, all of a sudden, Peter, you've got no shielding anymore. Yeah? Do you think that's a sensible engineering argument to put forward? Yeah? So I generally ignore shielding. Okay, so what we have to do is work out a force. Okay? Previously, we worked out a pressure. We now have to work out a force. As you all know, force is a pressure multiplied by an area. Okay? So if we design our hoarding looking at it per meter run, my area is going to be 2.5 meters high multiplied by 1 meter. We're designing it per meter. So my area is 2.5 by 1. Okay? So let's work out the force. So for Milford Haven, my pressure was 0.95, my area is 2.5, my CP net factor is 1.8, and shielding is 1.0. So hopefully, if my maths is correct, that's 4.275. Oxford, that's my pressure, area, CP net, shielding, 1.026. Okay, so we worked out the force. Are you all happy with these basic wind calculations? Yeah? And you do exactly the same thing for shutters, for cabins, for scaffolding, for false work, you know, any item of temporary works that you're designing that's affected by the wind. It's exactly the same process, no different at all. Right? Is everyone happy with it? Okay. Now, as I said earlier, the plywood sheeting and the horizontals, which we call rails, I'm not going to bother going through the design of that because you're all intelligent people. You design it exactly the same as we designed the shutter yesterday. So you put your wind pressure on it, you design your plywood spanning between your rails. Yeah? Your rails, you design exactly the same as we designed the secondaries yesterday, spanning between your uprights, your posts. And so I'm not going to waste your time doing that. What I want to focus on is designing the posts and the foundations. Okay? Now, what we're going to have is something that looks like this. So what we want to do is dig a hole, put some concrete in, and drop the post in. Okay? So we're going to dig a bit of a hole, put some concrete in, and design a post. And there's two things we're going to be looking at here. Number one, the post acting as a cantilever above the concrete. Okay? And secondly, the post and the foundation working together and the whole thing rotating something like that. Okay? So we've got two different considerations here. One, if you imagine my hands at a concrete, so we're going to assume the post is held rigidly by the concrete and the post acts as a cantilever above your concrete. And then we're looking at the post and the concrete working together. As we saw in that video, you know, the whole fence was moving. Okay? And the possibility of the post and the foundation failing together. Right? Now, we'll just do the example for Oxford. Okay? What we have is a wind pressure, a block of wind. Where's the centroid of the wind pressure? Where's the centroid of the wind pressure?
Halfway, holding.
Yeah. If it's a rectangle, the centroid is just in the middle. Okay? So my wind, so we worked out the force, okay, acts in the middle of that post. What's that lever arm above ground level? To force. Jump. Yeah, jump. We said our hoarding's going to be about 2.5 meters high, so that lever arm is 1.25 meters. Okay, 1.25 meters. Now, those of you who are familiar with crowd loading, the minimum crowd loading I would expect to be designing for, so let's call it C, okay, crowd loading, is 0.74 kilonewtons per meter run So the minimum we would design for is 0.74 kilonewtons per metre run. And those of you who are familiar with the handrail codes, that lever arm, where the crowd load is applied, is 1.2 metres above ground level. Who recognises that number in that lever arm? 0.74 at 1.2 metres. I think it's straight from the handrail code, Peter, isn't it? Okay. So you've got wind multiplied by a lever arm of 1.25 and crowd loading and a lever arm of 1.2. Okay. So we can calculate a bending moment, can't we? Yeah. FW times 1.25, C times 1.5. Now, we've got to have a guess at what centres we put these posts in. Try and work to multiples of sheets of plywood. Right? So try and put them in at either 1.22 or 2.44 spacing. Okay? So my first guess is, let's try those posts at 1.22, 2.44 spacing. Okay? So just have a guess, we'll put them in at 2.44 spacing. And because the hoarding is continuous, do you think we might need to allow for a bit of a continuity factor? What do you think an appropriate continuity factor might be here? 1.1? Yeah, because the hoarding it's a long line of hoarding. I'll take a factor of 1.1. Okay, so let's do a little calculation for this. So where's my... Okay, so ignore the Milford Haven one. Let's do the Oxford one. So remember we worked out the wind force was 1.206. My lever arm was 1.25. Multiplied by 2.44 metre spacing, plus my crowd loading of 0.74, 1.2 is the lever arm, 2.44 is the spacing, multiplied by a continuity factor of 1.1. So that gives me 5.8 kilonewton meters of bending in one of those posts. Okay? In the module, can you find figure 5, please? I can't remember what page it's on. Somebody find figure 5. It'll be about page 7 or 8, I think.
Page 8, yeah.
Page 8. Okay, so if you could have a quick look at page 8, please. Have you all managed to find figure 5? What you've got there, gentlemen, is a table of allowable bending moments for timber posts. Okay? So we've calculated the bending moment in our post is 5.8. So what we're looking for is something that gives us a safe bending moment more than 5.8. So tell me what we can use. Look at that table. What can we use? Give me some options.
Under about 200, 24.
Okay. Well, I've put here, so figure 5, I've put 150 by 150 or 2 by 75, but the C24 timbers. Have a look at 150 by 150. What does it tell you is the safe moment for that? So I can't hear, somebody's saying something, I can't hear you. Somebody give me an answer. Okay, you'll have to unmute. I can see people's lips moving, but I can't hear any words. 5.75, we got 5.8. Oh, come on, fellas, that's close enough, isn't it? Yeah? It's like England in the World Cup. That ball was, all the ball was over the line, wasn't it? Yeah?
I think that I'm thinking
6.294. 6.29.
And, yeah, if you look at the 225 by 75, that's probably quite a bit more, isn't it?
6.294.
There you go, easy. What I recommend you do, gentlemen, give your customer several options. Yeah? So you could say to them, you can use 150 by 150 or a 225 by 75 at 2.44 spacing. Or you could do another example and say, well, look, what about maybe you could use a 100 by 75, but they need to be at 1.22 spacing. Yeah? So I always try and give the customer 3 or 4 different options, let them price which one works out cheapest. Okay? Because sometimes they think, well, we'd rather use smaller timbers, but we'll put them at closer spacing. Some customers prefer to use bigger timbers at bigger spacing. Okay? But you see what I mean, gents? Give them 3 or 4 different options, let them price it. Okay? They can work out what they can get the best deal on. Sometimes they get better deals on smaller timbers, sometimes they get a better price on the bigger timbers. Okay? But give them 3 or 4 options. Okay? So are you happy that you understand how we get these allowable moments for the timbers?
Right. Is it critical for the sheet size? I mean, if you're putting rails on there and you could sort of close up the spacing, would it matter that the sheet size, work the sheet size?
It does, because it makes all the setting out a little bit easier. If you just work in multiples of sheets of ply, you don't have to. You don't. You could say, well, we'll put it at 2 meter spacing. Yeah. But on the whole, I think most people prefer to work in multiples of a sheet of plywood. You'll tend to find most hoardings with 2.44 spacing.
Right, a quick question. I am lost to what table you guys are using. Is it table C1 for softwood hoarding application, or is it figure 5 softwood properties?
Figure 5 softwood properties.
Oh, brilliant. Okay, good.
Okay. So we worked out a moment, I think, Derek, it was 5.8. So what I'm saying is 150 by 150 C24. I think somebody said the allowable moment was about 5.75 or something. I mean, that's pretty the 5.8, isn't it? And what was the allowable bending moment for a 225 by 75? It was about 6 point something, 6.2. Yeah. So give your customer several options. Give them 3 or 4 different options. Now, you'll see here, gentlemen, I've done an extra little calculation. This has happened to me on 1 occasion. Okay, in 30 odd years, this happened once. The health and safety mafia, okay, and I will call them a health and safety mafia. The safety guy for the site came along and he said, I don't want you using rough cut timber, because there is a risk people get splinters in their fingers. Okay? So what he wanted was for us to use something called PAR timber. Does anyone know what PAR timber is? Has anyone heard that term before? Planed all round. What they do is they take a timber and they put it through a planing machine, and normally the planing machine takes something like 1.5, maybe 2 millimeters off all the way round. So you end up with a nice smooth piece of timber. Okay? Do you know how expensive PAR timber is? Right? Because the safety guy was worried about people getting splinters. What's the obvious answer to that solution, to that problem? Instead of using PAR timber, what would you have suggested they do?
Gloves.
Even bloody gloves. Yeah. So you either spend an extra £5,000 on, planed timber for your hoarding, or you spend £2 on a pair of gloves. I mean, sometimes some of these safety people, you look at them and you think, well, you live in a hole. So if you ever need to do plain timber, which I don't recommend, I mean, why the hell would you use plain timber on a hoarding? What's the point of that? I've done a little calculation on basic stresses to prove the timber works when it's plain. Okay? So are we happy that we can design the post? It basically acts as a cantilever above ground. Right. The next thing we have to look at is the post and the foundation working together. Okay, so step one here is we're saying above the concrete, the post acts as a cantilever. So we've got to make sure the post doesn't break. We then look at the post and the foundation working together. And the reason we do that is because the ground, the soil, is not infinitely rigid. Okay? The ground has a bit of flexibility in it. Have any of you gents ever had to Have you ever watched anyone do it? Do you know how they do it? How would you get an old fence post out of your garden? If you've got a bit of a concrete... Yeah, absolutely, Peter. You do a bit of this with the fence post. Okay? You try and loosen the ground around the concrete, and eventually, hopefully, you can grab hold of it and pull it out of the ground. Yeah? Well, that's exactly what happens. You get this effect called post holing. So what happens is the post and the foundation both rotate about a point below the surface. Now, my analogy would be, have any of you gents ever designed a pile for horizontal loading? Foundation pile for horizontal loading. If you ever do, can I recommend this book? There's a new version of this. It's called Pile Design by a gentleman called Mike Tomlinson. Get Mike's book, and he talks about designing piles for horizontal loading. And what Mike talks about is when you apply a horizontal load to a pile, the ground will flex and the pile rotates. So if you apply a load there, the pile rotates about a point below the surface. Now, Mike calls it the position of virtual fixity. Okay? It's exactly the same theory for hoardings. Now, what we've done in the Temporary Works Forum is we've adapted a very, very old bit of theory and research. Okay? The simple reason, there is no proper code of practice or theory for the design of foundations to hoardings and fences. Okay? However, there is a code of practice for the design of foundations to lampposts. Yeah? With a lamppost, what we have is a post. We apply a load to it, for example, wind loading. And what we want to know is how big and how deep a foundation do we need to stop that lamppost falling over. Yeah? Does that sound pretty similar to a hoarding? Yeah? All we've got is a post. We apply a load to it, crowd loading, wind loading. Okay? And what we want to know is how big and deep should the foundation be to stop it falling over. Okay? So there is a code of practice for the design of lamppost foundations. It is called PD 6547. Okay? And there is a formula in it where we can work out it's a moment of resistance, an allowable bending moment for soils. Okay? Now, my master's was in geotechnics at Imperial College, and I was lectured by a gentleman called Professor Skempton, okay, one of the most famous names in soil mechanics. Dear old Professor Skempton will be turning in his grave at the very thought of a allowable bending moment for soils. Okay? But this is based on very old research carried out by the military, the British military. And somebody sent me the research a few years. Right, it's by a guy, you'll have to Google it, but I think his name is something like Colonel Theodore Wilberforce. Okay, and it's from about 1926. Okay? And I tell you what, if anyone called Colonel Theodore Wilberforce, well, do you know what? I'd listen to what he has to say. I mean, Gift, that's a name to be reckoned with, isn't it? And what this colonel came up with was this theory for designing lampposts. I think it started for telegraph poles. When they were putting telegraphs across the world, it was for design of foundations for telegraph poles. And what we can do is work out a moment of resistance of the ground. And the moment of resistance is a G factor, which depends on your soil. And there's only, according to this theory, there's only 3 different types of soils on the whole of this planet. Okay? Good soil, average soil, and poor soil. Gentlemen, how good would it be if geotechnics really was like that? Yeah? Imagine how much easier life would be if So, Stefan, you look at the ground and you've only got 3 different choices. Yeah? So you can look at the ground and say, yep, that's definitely 630, that stuff. Okay? So there's only 3 different types of soil. D is the diameter of the hole you're going to make. P is the depth of the hole, cubed, and we divide it by 10. So that's the formula we use. And this is the way the theory works. So what we're looking at is, can you see the post and the foundation rotating about this point here? Okay? And they call it the point of fixity. And the way you calculate where this point is you have a guess at a planting depth. And just have a guess. And say, well, half a metre, just have a guess. And that point is your depth divided by the square root of 2. So it's 1 over the square root of 2, 0.707. Okay? So let's do an example. So let's do the one for Oxford. So I'm going to have a guess at a hole diameter of 400, and I'm going to have a guess at a depth of 900. Right? It's just a guess. So my fulcrum is your planting depth divided by 1.414, which is, what's that, 1 over the square root of 2. So that tells me my point of fixity is 636 mil below the surface. Okay? So what we're saying is that point of fixity is 636 below the surface. So what happens to these lever arms now? What happens to that number and that number? They increase by 636. Okay? So all we do is we work out our bending moment again, but my lever arm is now 636 more. Okay? So what we have is my wind force, and the lever arm is 1.25 plus 636. There's your post centres, multiplied by your crowd loading. So same rule for your lever arm, multiplied by 2.44 centres, multiplied by your 1.1 continuity, and then we also add a global factor of safety on stability of 1.5. Okay, so the recommendation is you put an extra factor of safety, a global factor of safety of 1.5 on it. Okay, so we work out that calculation, and it tells us the moments for the post and the foundation is 13.3. So we now have to work out the resistance of the ground. Okay, now in Oxford the ground is really, really good. It's a really, really hard clay. So I'm going to classify it as 630. So we've got 630 multiplied by the diameter, which I had a guess at 0.4. I had a guess at a depth of 900. You work that out, it comes to 18.4, which is more than 13.3. So that foundation would be adequate. Okay? Now, I could rationalise it a little bit now. So I could go back and say, well, look, that difference is quite a lot. So what happens if I change that to 800? Yeah, save your customer a little bit of money, change it to 800, okay, and see if it works. Okay? So there is a little bit of trial and error here. You know, you might have to have 2 or 3 goes before you get to sort of like an optimum answer. Or if you're really clever, you start at the bottom and you sort of work the equation backwards to end up with a size, if you're really clever. Okay, so let me just run through that again. Let me just run through the theory. So you work out your wind. So remember, we've got these equations for working out the wind. So that's your basic pressure. That's your S wind. Okay, so you've got a topography factor, altitude, combined exposure factor. So you work out a pressure. You then work out, so when you're designing your plywood and your rails, you use that pressure. So force is pressure multiplied by area, multiplied by your CP net factor. So take it for the B zone, multiplied by shielding, which I normally take as 1. And then you've got your wind force times that lever arm. You might or might not have a crowd loading times that lever arm. And you look at your post acting as a cantilever above ground level. Okay? You then have a guess at a size of foundation. So have a guess at a diameter, have a guess at a depth. Work out where that point of fixity is. So it's your depth divided by 1 over the square root of 2, 1.414. Your lever arms increase. You then look at your post and the foundation working in bending, and then you compare it to the resistance of the ground, where you use that mg equals g times p times d cubed formula. Okay. Crowd loading on plywood and rails, yes. You do design for your rails for your plywood and rails for crowd loading. In the guide here, there's a couple of rules they tell you to do. So, for example, one of them is if you have a rail roughly where your crowd load is, you just design that rail to take crowd loading between the posts. Also, in the hoarding guide, they give you a series of different load combinations that you can consider. So, for example, it might say, well, what happens if you got the wind blowing from that side? Okay, so your crowd load's going that way, your wind load's going that way. Okay, would you agree that's probably the worst case if you've got wind load and crowd acting in the same direction? I think so. They also recommend you can consider, so sometimes you might have, you might be worried about some sort of impact loading, something hitting your hoarding. Maybe because you're pouring concrete or something nearby. You can then take a working wind, which they recommend as 200 newtons per square meter. You can then include an impact loading in your crowd loading. There's different load combinations that you can consider. Okay? The one I tend to design for is your maximum wind plus a minimum crowd loading. This is where I disagree with some of my colleagues on the hoarding guide. Okay, their argument is if you've got your maximum wind, it is pretty unlikely you're going to have a crowd load. Okay, because they say, well, if you've got something like maximum wind is about Beaufort scale 6 or 7, you can barely stand up in that. If you've got something like Beaufort scale 6 or 7 wind, you struggle to stand up in it. And so they say, well, why would you have a big wind with a crowd loading? My counter argument is, well, if you've got a really big wind, you've got more chance of your hoarding being hit by debris, branches, bins. There's going to be all sorts of stuff being blown around that's going to hit your hoarding. So I personally design for your maximum wind plus a minimum crowd load. It helps me sleep.
Right, sorry.
Go on, Dishy.
I have a couple of questions starting with the load. If it was in a sort of urban environment, in a sort of 30-mile-an-hour zone, for instance, would you have to design for any vehicle impact?
It's virtually impossible to design a hoarding for vehicle impact.
So would you exclude that in your condition of
I think so. So if you were worried about it, if your hoarding was very, very close up against a road, I would take additional measures to stop vehicles driving into it. For example, put some concrete barriers up or some big timber. So for example, on this particular hoarding here, can you see how they're managing the possibility of somebody driving into it?
The foundation.
Yeah.
Would you start with if you were given a commission to do a hoard, right? Would you then commission yourself, say, trial holes or something like that?
Yeah, absolutely. Absolutely. So in order for you to design a foundation, your site have to give you some idea of what the ground is. The easiest thing to do is phone up the site and say, get a couple of lads with shovels, dig a hole, tell me what you find.
Those factored in the various ground conditions.
Yeah.
You know, if you had waterlogged site, is there any alternative to using the G values?
You don't have to use this theory. You can go back to basic saw mechanics. And the other way of designing it, which is a bit more complex, it's a bit more difficult, is you use traditional active and passive earth pressures. And you go back to a theory by Carl Tetzage, okay, the father of saw mechanics, Carl Tetzage. And what you do, this is the way I've always designed, for example, king post systems. Okay? Where we've got something like this, so you can apply an active pressure to it. Okay? So your active pressure will be your coefficient of active pressure times gamma times the H, Ka gamma H. Now passive, with passive resistance. If I look at it in plan, okay, this is the way we would sort of design piles for horizontal loading. What you can look at is your passive resistance being developed over a length which is 3 times the diameter of your pile. Okay? Have you ever noticed when people design piles, the minimum pile spacing is 3 times the diameter of the pile? This is why. You don't put piles closer than 3 times the diameter of a pile. So if you're designing piles which are 1 meter wide, you put them at 3 meter spacing. So you could actually go back to basic saw mechanics and design from first principles. But this method is just easy. It's just an easy way to design a hoarding. Simple.
You have to allow for someone digging a trench. Would you allow for that?
So when we revised this, we took into account the possibility of a loss of passive resistance. So at the back of this, there is an example of what you do when there's somebody, you got a slope or somebody digs a trench next to your hoarding. Okay? So basically what we're recommending is that you reduce these G values. Okay? So get hold of this document, Bashir, just read this section about what you do when you've got a loss of passive. Okay? You thought of everything, fellas. Yeah? At least we've tried to.
Ray, could we backtrack a bit?
Okay.
A quick one. Could you explain in simple term continuity factor and to what if you're hoarding was that would cause your equations to change, I'm assuming. And that's about it, to be honest.
Continuity factor. Do you know we said yesterday when we had this sort of loading condition? Basically what we have is a load, so that's my hoarding, these arrows are the posts. So in effect we have continuous structure. Yeah? And we said the continuity factor we normally take here is an extra 10%. So if I design for continuity, I'm being conservative. Yeah? Okay. And what was the second one you asked about, Derek?
If the hoarding was curved, if it was curved.
Curved. Why the hell would you want a curved hoarding?
If you have a circular site in the middle of the city, I've seen that before, and you have to put the hoarding circular. Would the equations change? Especially your wind interaction.
It's not going to be a tight radius for one simple reason. You're limited by what sort of radius you can bend plywood. Yeah?
Okay, I get you.
If you look in the formwork guide, they give you rules about what sort of radius you can bend plywood to. Now you can get it to a tighter radius. For example, if you're doing a curved concrete wall, okay, does anyone know how you can get plywood to a very, very tight radius? You can bend it to a tight radius. Right, what you do is you get a very, very skilled operative, and what they do is they cut notches into the back of your plywood, and then you can concertina it to a tighter radius. Okay? That is massively labour intensive. It's a real skilled job. It is massively expensive. I cannot imagine any site spending that sort of money just on a hoarding. Okay? It is hugely labour intensive. You imagine somebody getting a skills or router, having to go to the back of each sheet of plywood so you can bend it. And you might even have to steam bend it, because the tendency then will be is your plywood will want to spring back. So you might have to bend it under steam. Okay? Nobody's going to spend that sort of money.
Ray, just on the continuity factors, where could you find some more information about that? Because I know we talked about the 10%, but there was also a 25% increase as well.
Yeah, Steel Designer's Manual. Have you all heard of the Steel Designer's Manual? It's my copy of it. Yeah? Well, this is a handy pocket version of it. It's like a brick, isn't it? But what you have is a whole load of the... I mean, I just photocopy it out of here, to be honest with you. You've got all of these. Yeah? So get a copy of the Steel Designer's Manual, and you've got all the rules about continuity factors in there. It's basic structural engineering continuity factors. Okay, gentlemen. What I would like you guys to do, have a go at an example. And the example you're going to have a go at, let's see if I can find an example of this. Just bear with me for one moment. So we'll have a go at this, and then we'll stop for a cup of tea. Now, what I would like you to do is have a go at, right, it's 085, RKF 85. This is what it looks like. I'll just share my screen with you. How many of you gents have found section 085? This is what we're looking for. Okay. This particular hoarding is in York. Now, because this example, I think I did it before the new guide came out. I think you can use the old factors for probability, the old 0.83 squared. Okay, if I was doing this, and you know, I need to revise this example, I would now change that probability factor. So if it was you know, more than a year, it would be unity. If it's less than a year, it will be 0.9 squared. Okay, but I think for the sake of this, use the old 0.83 factor. So work out your wind, and then don't worry about your plywood and your rails. Don't worry about those. can you just design your posts and your foundations? Okay, so do what we were doing here. So tell me, you know, what posts you need, what foundation is. So work out your wind, work out your posts, work out your foundations. Don't worry about the rails and the plywood. We'll give you 15 minutes to have a go at that, and then we could stop for a cup of tea. Those of you who not sure where York is, it's actually on the wind map. So if you look at the wind map, it's in. If you know, if you head towards Scotland, York is, you know, before you get to Scotland. If you're not familiar with a map of the UK.
終於可以暫停啦。都未播個人又唔喺度。啊，錄影㗎嘛〜